One of the most classic examples of a series that you encounter in calculus or analysis is the harmonic series, which is the sum of all the reciprocals of the natural numbers. So 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and so on. And it's a well-known fact that this series actually goes to infinity. It diverges. But if we remove those numbers with a 9 in their representations, so 9, 19, 29, 92, 943, then the series actually converges. Huh? How is that possible? Such a series has been dubbed a Kempner series after the mathematician who wrote a paper about it. That was back in 1914. But this is really unintuitive to me, because even if we remove all of the odd numbers, the harmonic series still diverges. So how can removing all the 9s change that? So that's what I want to talk about in this video. So we're going to talk briefly about why the harmonic series diverges, and then we're going to jump into Kempner's argument here. Okay, so why does the harmonic series diverge? So this is a classic argument that you've seen before if you've taken series, but if you haven't, then let's consider this. So the sum of 1 over n from n equals 1 to infinity is a sum like 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, and so on. And I'm going to bracket some of these terms together and you'll see why. So I claim this sum is larger than 1 over 1 plus 1 over 2 plus 1 over 4 plus 1 over 4. So notice that 1 over 3 is larger than 1 over 4. So I can just say that this is larger than 1 over 4 plus 1 over 4. And now for each of the terms in this second bracket, I'm going to say that they're larger than 1 over 8. So 1 over 5 is larger than 1 over 8. 1 over 6 is larger than 1 over 8. 1 over 7 is larger than 1 over 8. And then we just have a 1 over 8. Okay, so I'm going to keep bracketing and keep using this pattern. So the next brackets are going to have 1 over 16, 1 over 16. And we can definitely say that our harmonic series is larger than that new series that we just made. But if we take a look at the brackets that we have, we see that actually they all add up to a half. So in other words, this new series is 1 plus a half, plus a half, plus a half, plus a half, and so on, which clearly goes to infinity. If we're adding up a half infinitely many times, that's not going to add up to anything finite. So that's a classic argument to show why the harmonic series should diverge. And I claim that even if we remove all the odd numbers, it still diverges. And one easy way to see that is just, well, if we're summing up 1 over 2 n's, so in other words, all the even numbers, then that should basically just be a half times the harmonic series. You can imagine throwing that 1 over 2 in, which we know is infinity. So removing all the odd numbers doesn't change the divergence. But somehow removing all numbers with a 9 makes this converge. So let's see how. Our strategy is going to be to break it into pieces. So we're going to consider the ones, the tens, the hundreds, the thousands. And for each of those, we're going to see how many numbers do not include a 9 in them. So let's just start with the ones. If I consider the terms 1 plus 1 half all the way to plus 1 over 8, those are all kind of the 1 terms that don't have a 9 in it. That's less than 1 plus 1 plus 1 plus all the way up to plus 1, 8 times. So that's less than 8, clearly. Okay, so that's handled. It's a pretty crude upper bound, but we've got the ones handled. Now the question is, how many numbers without a 9 appear from 10 to 99? Well, in each batch of 10, there is one 9. So like 19, 29, 39, 49. And we can ignore all the numbers from 90 to 99. So in other words, from 10 to 99, we have 8 lots of 9 numbers that do not contain a 9. Of course, we can just remove 90 to 99. So we just have 10 to 18, which is 9 numbers, 20 to 28, which is 9 numbers, and so forth, 8 times. So we have 8 times 9 of them, which is 72. And we can replace each of those reciprocals with 1 over 10, just as a crude upper bound again. So in other words, 1 over 10 plus 1 over 11 plus all the way up to 1 over 88. If we remove all the 9s that appear, then that is less than 1 over 10 plus 1 over 10 all the way up to 1 over 10, but 8 times 9 times. And I can add all those up and I get 8 times 9 divided by 10. So again, this is another crude upper bound, but we'll start to see a pattern in a second. Okay, so now in each of the hundreds, we have a similar sort of pattern going on. So from 100 to 199, 200 to 299, we must have 8 times 9 nines in them, but we can ignore all the numbers from 900 to 999. So in fact, we just get 8 times 9, but 8 times. So for the 100, 200, all the way up to 800. And in fact, that gives us 8 times 8 times 9 numbers from 100 to 999 with no nines in it. So we can do the exact same trick. So now I'm going to write 1 over 100 plus 1 over 101 plus 1 over 102 all the way up to 1 over 888. And we're going to remove all the nines therein. That's going to be less than 1 over 100 plus 1 over 100 plus 1 over 100 all the way up to 1 over 100. But 8 squared times 9 times, or 8 times 8 times 9 times, for a total of 8 times 8 times 9 divided by 100. But I can write that 100 as 10 squared, so maybe we see a pattern of what's going on here. So we get from generalizing this trick that the Kempner series is less than 8, okay, well that was for the ones, plus the sum from k equals 1 to infinity of 8 to the k times 9 divided by 10 to the k. Okay, well, that's just 8 plus 9 times the sum from k equals 1 to infinity of 8 over 10 to the k. And that looks like a geometric series, so we can add that up. That's going to be equal to 8 plus 9 times 1 over 1 minus 8 over 10, which is 8 plus 9 times 5, which is 8 plus 45, which is 53. Well, that's definitely less than infinity. So in other words, since our sum is less than 53, and that's less than infinity, our sum converges. So you might have noticed that in this proof, we didn't actually use anything about the number 9. So the same argument works equally well for omitting the 3's, for example. And actually, you can generalize this to omitting strings of digits. So for example, this type of series still converges if we omit all numbers containing 3, 1, 4, 1, 5, 9 in their representation. So something for you to think about. Can you see how to run this argument generalizing to strings of digits? It gets a little bit trickier, but same idea applies. And if you want to understand more about convergence, the simplest setting to understand that in is metric spaces. So if you want to learn more about that, check out this video that I made.